Hi everyone, my name is Shreya Anand. I'm a third year graduate student at Caltech and I work with Mansi Kasliwal. Today I'll be talking to you about ZTF alerts and the alert filtering process. How do we get from raw survey images to transient discovery? So this is going to be much of a review for most of you, but just a reminder that the Zwicky transient facility, which is operated by Caltech, is a 48 square degree field of view imager mounted on the Palomar 48-inch telescope, and it scans the entire sky in the course over the course of 2 to 3 days. So this imager has two main filters that it performs surveys with. It also has a third I-band filter. The main two filters are G and R, and it reaches a limiting magnitude of 20.5 in its normal survey operations. So here you can see, for context, and I find this quite fun, the fact that three adults can actually fit right here in the instrument, which is very interesting. So the ZTF survey time is divided primarily into three different surveys. One is the public ZTF survey, also known as MSIP, that comprises 40% of ZTF's time. The second is ZTF collaboration survey, or the partnership survey, which takes up 40% of ZTF's time. And finally, the Caltech survey, which takes up 20% of the time. The partnership survey also includes the opportunity to perform target of opportunity triggers, which are triggers that interrupt the normal survey operations to look at a particular region of the sky due to some kind of external trigger, such as a gravitational wave signal, gamma ray burst, or a neutrino trigger. And this is only available to those of us who are within the ZTF collaboration, and the Caltech survey is available only to Caltech members. So here is a map showing ZTF R-band coverage over the sky. So one thing you'll notice is that the tilings only reach about -30 declination, and that's because ZTF has hard limits on where it can look in the sky due to observability constraints. And furthermore, as you'll see in a couple of slides, due to different survey operations, there are certain regions that are observed at different cadences. So you can also divide ZTF's time into different science cases broadly. So there's the galactic plane survey, which aims at looking primarily at the galactic plane at a certain cadence. And this is for the discovery of certain types of galactic sources, novae, binaries, and CVs, for example. In addition, the Northern Sky Survey aims to try to get in an unbiased view of the entire northern sky. And that is what we quote as the nominal 2 to 3 day cadence. And finally, there's the extragalactic high cadence survey, which attempts to look at um, one subset of fields at a high cadence. And this is aimed at the systematic discovery of fast fading transients or fast evolving transients. And amongst those are kilonovae, which is what I work on. So here you can see how the requested how the number of observations are plotted as a function of fraction of completed requested observations. But in addition, you can see the effect of cadence here. So this is fraction of observations as a function of night between observations. And you can see that the galactic plane survey occurs at a much higher cadence because it's looking at a pretty narrow region of the sky as compared to the Northern Sky Survey, which attempts to survey the entire northern sky. So the main takeaway from this slide is really that there are a lot of different moving parts in the ZTF survey, and that requires a very efficient and automated scheduling system that allows for all of these different components, both different tiers of accessibility as well as different science objectives, different surveys that are aimed at getting out different types of science. So once we have obtained all of these images, what do we do with them? So the ZTF system works to detect flux transient alerts, which are objects that change in brightness over time in ZTF images. And these alerts are distributed automatically in a very efficient fashion. And it's quite different from the classical setup where you would take an image, perhaps take a reference image many days later after your object has faded, perform image subtraction, and then perform your own analysis. So why doesn't ZTF provide us with just the raw images themselves? Why is there this whole system of alerts? Well, we have to understand that in the case of the ZTF survey, there are three main factors here. One is the sheer volume of data. If you consider that ZTF is processing thousands of images or taking thousands of images per day that need to be processed, then you really need an automated system to discover new objects. The second is recognizing that transients fade fast over time. So if you want to also be able to systematically discover transients that fade over the course of days and weeks, then time is of essence. And so you need an automated system. And third, when you're performing a large scale analysis, you might want to reprocess all of the light curves. For example, you may want to weed out some of the transients that you initially thought were interesting that are instead flaring active galactic nuclei, which have historic light curves. And so you really need the light curve history to be quickly accessible in data archives. And so you need an automated alert system in order to perform these things. And so this is a bit of a complicated figure, but I'll try to do it as much justice as I can. But the main idea is that it describes how we get from raw ZTF images to transients. So here we have the P48 Palomar 48-inch telescope and the ZTF camera, which is taking all of these images across the sky. Then it gets ingested into the IPAC database, which stores all of the images and splits them up according to position. The raw images and metadata are stored. And then, as we know with any kind of image processing, we need to perform calibration, such as flat fielding and bias subtraction. And so that occurs in its own pipeline. And then that's fed in turn to this instrumental photometric calibration pipeline, and further fed into which produces the final science quality images. And then we get to real-time image subtraction. There's another element that I have to talk about here, which is that how does ZTF obtain those reference images for subtraction? Normally, you might think about doing image subtraction with a reference catalog like PanStars or STSS. However, in the case of ZTF, you need to make sure that every single position that ZTF is imaging has a reference epoch, has a reference image that goes deeper than the science image. And thus, ZTF spent some time early in the survey uh, dedicated to building up a deep reference grid so that even if you decide to trigger a target of opportunity observation that goes deeper than the nominal 30-second survey exposure, you would have a reference that's deep enough to perform the image subtraction. And so there's epochal images and catalogs that go into building up this reference grid, which is also fed into the subtraction pipeline. And finally, those images are fed to the alert brokers. So the alert brokers produce from these subtractions, you get alerts for each object, and you end up with alert packets because you have multiple detections for a given object over the course of days and weeks. And so these are distributed out to the public um, using the ZTF alert distribution service. And furthermore, they are then stored in various different databases for us to perform science within ZTF. And so um, some groups are interested in discovery of asteroids and other moving objects. And so some of that data gets put into the ZTF depot and ZTF moving object discovery engine. And then the light curves, or the discoveries of asteroids and other solar system objects, have their own database. However, if you're interested in transients like supernovae, you might, or variable stars even, you go through this light curve pipeline, which then produces light curves from from the discrete alerts, and then those light curves and metadata get stored in your respective galactic marshal or into your Fritz transient marshal. So now I'll just talk a little bit about the different alert brokers that that go into this that were described in this pipeline. So the main purpose of the alert brokers is to distribute the alerts in a systematic fashion to the rest of the scientific community and to the public. So we have a couple of different examples here: Alersi, Antares, Lasser, Ampel, and Fink as the alerts that are currently being used and that will probably be used in the era of Vera Rubin Observatory. So here's an example of one of the alert brokers called Fink. You have a framework where the alerts from, in this case, Vera Rubin Observatory are stored. They are processed quickly, put into storage, and then from the storage, they are transported to this scientific portal that is then accessible to the public. And the main need for this is, well, alert enrichment, filtering, and redistribution. So the idea is that the scientific community not only wants to receive the alerts of different objects that would help build up the light curve, but they also want to know more about the objects themselves in order to perform their science. And so alert enrichment involves potentially cross-matching to different galaxy catalogs, cross-matching to various perhaps multi-messenger sources or multi-wavelength detections, and classification of early light curves using machine learning algorithms. Further filtering from the initial instrument, right? that would allow you to select the candidates that are just relevant for your science case, historical data, which we talked about, and then systematic redistribution. So it would send out a reduced stream of alerts and provide a user-friendly web interface and API for performing customized queries. So these alert brokers are very useful for getting from ZTF data to the scientific community. So now I'll talk a little bit about this image processing pipeline. The main idea is, again, to understand how do we get from the exposures to the alerts. So, so this is taken from the ZTF web website which has observation logs from every night. So here you have the exposure time, the time at which a given image was taken. Now ZTF has a fixed grid system, which means that the entire sky that is visible to ZTF is divided into a grid, basically, which has several different fields, and each field has 64 quadrants. And so this is an image of the ZTF primary grid in different filters. And so, so here what you're seeing is, for a given field, all of the different, many different quadrants that were observed, and the positions of each of those quadrants. And here are the number of alert packets that were produced in every single quadrant. So this is how many different alerts were detected. Finally, there's a program ID, which we talked about earlier, the MSIP partnership or Caltech. So in this case, this is the public survey, the exposure ID, and then it's a very large table. So here's a continuation. This is the filter in which the observations were taken, and the difference and science limiting magnitudes, which dictate the depth of the image, the seeing and full width half max, which dictate the quality of the images, the exposure time, and then finally the processing success. So was the image subtracted? Was image subtraction conducted successfully? And that really goes to dictate whether or not alerts were produced in that given field or in that CCD. So here we have the new science, the science image of a given transient. This one is called ZTF21 ABJYIIW. It's a supernova 2b. You see this nice detection here in this large spiral galaxy. In the reference, there is nothing at the position, which is very good. And then when you perform the image subtraction successfully, you get this point source here. And so from that point source, you get alerts. So is that it? Are we done once we have this lovely subtraction? The answer is not really. We still have to make sure that whatever we detected is real or astrophysical, right? We can do that. There are already machine learning classifiers in place for that. We want to make sure that there's no star underneath that's flaring and pretending to be a transient. There's no bright star that is overflowing its neighboring pixels and creating some kind of artifacts. We want to eliminate moving objects, especially if we're interested in supernovae. We don't want to confuse supernovae with moving objects. And we want to make sure there's no previous history. So maybe we want to make sure that it's not just the galaxy that's flaring, and there's actually an explosion that occurred at that position. And finally, we get our set of transient candidates. So I thought it would be fun to show this example here of one of the false positives that we detected during our gravitational wave follow-up. So here you can see um, one about 1 day before the merger, at the position of our detected transient candidate, there was nothing there, but we detected it on the second day. However, um, taking a much closer look at the images, we see that there is this blob of brightness here right next to the position of the transient. And so it has actually moved into the yellow circle. So this is a moving object along its trajectory that we happened to detect. So that's an example of an asteroid that's pretending to be a transient. Now, um, finally, once we have our list of candidates, we want to classify them. We want to know what they are, right? And so this uh, occurs in a very expedited timescale, for example, during a gravitational wave follow-up campaign. I'm giving this example because this is something close to heart. I work on gravitational wave follow-up. And so we request rapid imaging of a given region of interest dictated by the sky maps in which we're searching. We request for multiple visits. And then in the same night, we get the image subtraction results. We perform the filtering in real time to remove all the non-transients, and we apply additional filters to look for the types of transients that are fast fading that we're very interested in, red and fast fading. The light curves build up over the course of hours to days. And then finally, we end up with a list of transients that are very interesting, and we need to know what they are. So we take spectra, we perform spectroscopic classification. So here are two examples of interesting transients that we detected in our follow-up. So here you have the new image again. You see the detections here, where there was nothing at the reference position. The light curves you can see in early time, we see rapid evolution, which is why these transients were interesting. But when you take a spectrum, you know what they are. So in this case, this was a type 2 supernova. You can see H alpha pretty clearly. And then here we see magnesium 2 lines, which show that this is in fact a long GRB afterglow detected cosmologically at Z of 1.26. This is a very exciting discovery. So another example, and this really relies on the systematic nature of ZTF alerts, is the Bright Transient Survey. So this is in fact the largest spectroscopic supernova survey ever conducted. The aim of this experiment is to get spectra of every single time-varying, non-moving object brighter than 18.5 mag in order to get a complete picture of the supernovae in the northern sky, the bright supernovae in the northern sky, and other types of transients. And so you can see here the different supernovae detected as a function of sky position. You'll see this white region here, which corresponds to the galactic plane, and that it's white here because it's very hard to detect transients when there's a lot of extinction from the galactic plane and other kinds of contaminant objects. And then we see a phase space plot. So here it's peak absolute magnitude as a function of rest frame duration above half max. And you can see where the transients are falling in this phase space based on the transients that were detected in this survey. And so by building this complete set of objects, you can do all kinds of additional science and know that you have a near complete sample, which is really fantastic. So so let me walk through this quick example here, showing how supernova discovery actually works for a survey like a bright transient survey. So let me stop sharing for a moment. And all right. So, so you'll see here that there are many different customized filters that you can apply when you're playing with this page. And this page is available to anyone. So I encourage you to go ahead and play with it. So the idea is that all of these transients were detected as a part of the survey, and you can further customize it. So if we say, okay, I want a supernova like light curve, and I want a host galaxy cross-matched to it. And then we want the cutout from ZTF and the host. We would like the light curves, the discovery date. And finally, we want to apply a cut that says only the recent supernovae. So within detections within the last 20 days. And we click submit. So then we get this beautiful list of various different candidates. And we can further select for the ones that we're particularly interested in. For example, in my case, I'm interested in 1C broadline supernovae. So I can look for all of the 1C broadline supernovae that are detected as a part of BTS, and then go off and do my own science with them. So I encourage you to play with this page here. And in addition, I encourage you to also check out ZTF Query for retrieving images, querying for alerts, and constructing the light curves yourself, because the public data is actually accessible to anyone. So thank you very much. I hope you enjoyed this presentation and have fun playing with ZTF alerts and filtering.